This is Vodcast 10A. In this unit, we're going to be talking about thermodynamics and thermochemistry. There's 4 videos in this unit. The first one we're going to do talks all about heat, temperature, and specific heat. The second one is entropy and enthalpy. The third one will do calculations with phase changes. And video D, we're going to talk about phase diagrams. So, thermochemistry. Here's our overview. We're going to be talking about energy, which is the ability to cause change. Temperature comes back, which measures average kinetic energy. Heat, slightly different from temperature, measures total kinetic energy. We'll be doing calculations with heat capacity, which is the amount of heat required to raise the temperature of an object. We're also going to be talking about enthalpy and entropy, which is the energy content of a system, and entropy measures the disorder level of a system. And then there's something called Gibbs free energy, which allows us to predict if something is going to be spontaneous or not. First, energy. Your definition is the ability to do work or produce heat. In a physics class, you would talk more about work. You're pushing something, you're pulling something. In chemistry, we talk about heat. Something is either endothermic or exothermic. Heat is either coming into the system or going out of the system. We studied energy before, and we studied there was a law that was the conservation of energy law, that energy cannot be destroyed or created, it's only transferred. You can only move it, convert it, or transferred from one substance to another. Energy is composed of both heat and work. Again, we're going to focus on heat, which is represented by the letter Q, which is the quantity of thermal energy. Kinetic energy depends on the movement of the particles, and potential energy is stored in the bonds. Our unit is going to be the joule. The unit for energy is the joule, which can also be converted to calories, is what you may have heard of before in terms of food and such. There are 4.184 kilojoules equal to 1 calorie, and there are 1,000 joules in a kilojoule. We'll need those conversions when we start our calculations. How do we measure temperature? We've seen this slide before. This is a review. Celsius is the metric measurement for temperature. Kelvin is the international standard unit, how we measure temperature, and Fahrenheit is the one that we use. So your conversions are listed right here. There are 3 different scales, Kelvin, Celsius, and Fahrenheit, and we can look at some different numbers on here. Where water freezes is 32 Fahrenheit, or 0 Celsius, or 273 Kelvin. Where water boils, 212 Fahrenheit, 100 degrees Celsius, 373 Kelvin. And way down here, something called absolute zero, where all motion of all particles would cease to happen, there's no motion whatsoever, is 0 on the Kelvin scale. So Kelvin has all positive numbers. It's negative 273 on the Celsius scale, and it's negative 460 on the Fahrenheit scale. So you should be pretty familiar already with converting temperatures, but let's try these. Number 1, convert 25 degrees Celsius to Kelvin. If I plug in 25 for my Celsius, 25 plus 273 is 298 Kelvin. Number 2, convert 300 Kelvin to Celsius. Now I'm plugging in 300 Kelvin. 300 equals Celsius plus 273. I have to subtract 273 from both sides, so I get 27 degrees Celsius. And if I want to convert 80 degrees Fahrenheit, which is a nice warm day outside, into Celsius, I'm going to use this equation. I plug in 80 Fahrenheit. 80 equals 1.8 Celsius plus 32. Order of operations tells me I first have to subtract 80 minus 32 is 48. 48 equals 1.8 Celsius. To get rid of the Celsius, I divide both sides by 1.8. 48 divided by 1.8, keeping two significant figures. If you punch that into your calculator, it should be 27 degrees Celsius. So by now you should be able to convert temperatures, Kelvin, Celsius, and Fahrenheit. Temperature versus heat. We're going to talk about this again. They are not the same thing. Heat is transferred between objects because of a temperature difference. The temperature is an intensity. It's measured in Kelvin as the standard, or Celsius, or Fahrenheit. It's intensive. It's an intensity. It does not depend on the quantity of matter. It doesn't depend how much you have. It's already in there. You could have a teaspoonful of boiling water at 100 degrees Celsius, or a big bucket full of boiling water at 100 degrees Celsius, and they're at the same temperature. Temperature measures the average kinetic energy. How is heat different? Heat is a quantity. It's extensive. It does matter how much stuff you have. If you have a spoonful of boiling water, or you have a huge bucket full of boiling water, even though they're at the same temperature, there's a different amount of heat in the smaller one than there is in the larger quantity. If you think of which one would hurt more if it spilled on you, obviously the bigger, the more quantity, this is extensive, the more quantity you have, the more heat you have, the more dangerous it could be. Heat is either measured in joules, or calories, or kilojoules, and there's your conversion. And heat is a measure of the total kinetic energy. Temperature was average, heat is total. That's why it depends on the quantity, because it measures total and not average. Here's our equation for this unit. The heat capacity is equal to the amount of heat that is absorbed by the material divided by the increase in temperature. So the specific heat of a substance is the amount of heat needed to raise the temperature of 1 gram of stuff by 1 degree. So our units are either calories over gram times degree, or joules over gram times degree. How much energy is needed to raise 1 gram of a substance by 1 degree Celsius? That's heat capacity. Here's our equation. Q stands for the total heat in calories or joules. So your units can change. But either way, Q is the heat, the total amount of heat, either measured in calories or joules. And Q, or the heat, is equal to N. N is the same thing as the last unit. N is the amount. N can either be measured in grams or moles. And we know our snowman conversion to convert between grams and moles. So if I give it to you in one and it requires the other, you just do a one-step FLM mole calc to change it from either grams to moles or moles to grams. C, this is the new piece. This is the specific heat. Measured in calories over gram times degrees Celsius. So make sure all of your units agree. Just like we did in the gas unit, make sure your Q is in calories, your mass is in grams, and your temperature, down here, is in degrees Celsius. The change in temperature, measured in degrees Celsius, this little triangle means change in, delta. Change means final temperature, minus initial temperature. The only curveball that I can give you for temperature is if I give them to you in Kelvin or Fahrenheit. You'll have to convert them to Celsius and then subtract. So we're going to use this new equation, Q equals NC delta T, Q equals NCAT. That's our thermodynamics equation with heat capacity, specific heat, to solve some problems. Problem number 1. How much heat? Which variable is heat? I'm solving for Q. How much heat is needed to raise the temperature of 150 grams? N is 150 grams of water from 25 to 90 degrees Celsius. There's my temperature change. Remember, delta T equals final minus initial. My final temperature is 90. 90 minus 25 is 65 degrees. So in my delta T, I have 65.0 degrees Celsius. And now I need my C value. C value stood for specific heat, which is given to me as 4.184 joules over gram times degrees Celsius. Again, watch your units cancel. Here's gram. Gram cancels with gram. Celsius cancels with Celsius. When I calculate my answer, my units are going to be in joules. And if you plug this in your calculator, keeping 3 significant figures, I get 40,800 joules. That's how much energy it would take to raise 150 grams of water from 25 to 90 degrees Celsius. Number 2. If 45 joules, joules is a measurement of heat, right? That's Q. So I know I have 45 joules. 0.0. 45, 3 significant figures. 0.0 joules raises the temperature of a piece of silver by 67.9 degrees Celsius. Now my subtraction's already been done for me. I don't have to do final minus initial. 67.9 degrees Celsius is my delta T. That's my change in temperature. I'm raising the temperature. What is the mass of the silver? Mass is N. That's what I'm solving for. I also need my specific heat value, or my C. The specific heat of silver is 0.235 joules over gram times degree. Again, watch your units cancel. Joules will cancel with joules. Degrees Celsius cancels with degrees Celsius. When I solve this equation, my answer is going to come out in grams with the unit. Now, how do I get N by itself? In order to isolate N on the right side, I have to divide both sides by 0.35 and 67.9. So 45 joules divided by 0.235 divided by 67.9. And my answer is going to be, again, in grams, and you should get 2.82 grams of silver. So again, using algebra equations to solve, Q equals NC delta T. It'll tell you what's given, what you're solving for. Don't forget delta T is the change in temperature, final minus initial. N is in grams. Whatever your specific heat units are, everything should cancel out.